This company have improved Kafka's producer's rights by over 82% by switching file systems. But the way they got there is beautifully written in this technical blog that I want to share with you in this episode of the Backend Engineering Show. How about we jump into it? So this company is called Allegro. The title of this blog is Unlocking Kafka's Potential by Tackling Tail Latency with eBPF. Not the best clickbait title if you ask me, but the content is beautiful, the way they went into details of showing them, showing us how they got there by using out-of-the-box tooling. They rarely, go and recompile source code. Also, Kafka is open source. They could have recompiled and did all this stuff, but no, they used out-of-the-box tooling, which I love. This is a way to look transparently into things. They traced Kafka. They parsed the protocols of Kafka, the TCP binary protocol they use. The protocol, the binary protocol that Kafka uses on top of TCP. TCP is its own, it's a protocol. But Kafka uses its own binary on top of that. They parsed that to find out the request and the slow request and responses. Then they matched that with the kernel. They traced the kernel to find out what is the corresponding, what happened. And they found out that there is a slowdown in the file system, which is called ext4. Then they dove into the kernel of all these calls, the file system calls, and they found exactly where the problem is. Spoiler alert, it was a lock when it comes to a commit to those file systems. They eventually did some certain configuration to the file system to improve those latencies, and they eventually decided to switch the file system altogether to a new file system called XFS, which gave them this beautiful boost, 82%. Now, so they didn't go all the way and explain why XFS is faster in that particular case than ext4. So take that word grain of salt. This does not mean ext4 is bad. It's just it depends on the use cases. So let's dive into this blog goodies. Kafka. We all know Kafka, do we? I made a video years ago. That video needs a desperate refresh. Kafka is this beautiful publish subscribe system. It's allow for asynchronous consumption. Yeah, this is Kafka. So it is the asynchronous way of communication. It's one of the design pattern I like to explain in my backend course, where usually when you send a request, like how do you consume stuff? From two different parties. I have something to give you. I have something to read. There's two entities. They need to read from each other. How do you do that? You can let them talk to each other, but they will be completely out of sync. Sometimes I have data to publish. I have something to send, but the client is not ready to consume. This is not always one-to-one. So people invented this idea. It's like, all right, let's take your data, publish it somewhere, and then forget about it. That's it. Forget about who's consuming it, who's gonna read it. Forget about it. Just move on, right? So you're publishing to something called a broker, and then or producing. That's the word used. And then there's a consumer on the other end that on its pace, on its own pace, consumes those the content that you publish. And there is so many things you can do here. How to consume it? Do you want it push? Do you want long poll? Do you want it short poll? Do you just do it on demand? Whenever I feel like it, I'm gonna request. I'm not interested in latest update. And all of this stuff as I explained it. So that's Kafka. You publish, you produce, so you write to that broker. There is a write. So that gives us back to this. We're writing to this beautiful broker. And this is where things get slower. Yeah. And I'm not gonna read every single word here because first of all, it's gonna take me being slow. It's gonna take me 7 hours to read. Second, I really need to give credit to those guys. You need to go visit this page because if I read the whole thing, then there is no reason for you to check the blog, is it? right? And I apologize, I cannot read the names. I'll try my best. The authors, always credit the authors. Masej Moski, these are European names, of course. Piotr Rizosko. I apologize from the bottom of my kokoroni. Okay, so I produce requests, and they saw that these requests are suffering. You know, these requests are being suffered. Look at this. Look at all this stuff. What is this? What is this? 3 seconds. Yikesy. 3 seconds to write, to produce to the Kafka broker. You know, this is not consumption. Consumption is read only, right? I mean, there is a little bit of a write when you consume. You move the position of where you're writing. So there's a tiny write, but there is nothing really a problem when it comes to reading. So there is no problem with reading. There's the most problem with writing, right? That's that they faced, right? Of course, there can be read problems, but they did not see it. They didn't talk about it here. So we're writing, we're seeing at P999. I talk about these latencies, but yeah. So they found that of course, every time you add a 9, you're picking up those slower requests. You know, so this 999 is 3 and 2 9s. I think it's 1 second, which is this somewhere over here. And I have a video explaining these latencies, like 999. Yeah, so you have 3 seconds, and this is slow, of course, right? In the worst case scenario. So what did they do? So that's the problem. We know the problem. Well, they just know that the producer is slow. They don't know what request. They have no idea. Zero transparency from Kafka. The first thing that they found, all right, we need to trace Kafka. And guess what? I was surprised. There is no metrics when it comes to Kafka that captures, hey, this, we sent a request. We're logging the request. I'm pretty sure there is. They might have missed this, because I'll be surprised to see that there is no logging when it comes to Kafka. When it comes to, hey, someone just made a produce request to this message, to this topic, to this partition, and it took this much, and it arrives. There is nothing like that. Apparently, they had to roll their own, and this is March 2024. So maybe something like that doesn't exist. Is Kafka that fast that nobody actually decided to write something like that? I'm surprised. You Kafka experts, let me know in the comment section or below. So we have a slowdown. So they say, hey, let's write a tool that parses the protocol. I love this. I absolutely love this. Look at this. They said, all right, well, the Kafka is basically built on TCP. You don't really get much options, really, right? Either TCP or UDP, to be honest. You don't get much options. So it's a binary protocol. It's its own protocol. And what did I say? What do I keep saying about requests and responses? You know, the concept of a request and response doesn't exist in TCP. It's a higher level application level, in this case, Kafka. So you need to understand what a request is and what a response is. And they had to parse that. They have to read these segments, read, and start parsing the protocols. Oh, we just got something, producer. So they put this code on the broker side, right? Oh, just got a request, right? So they built a parser, essentially. And then they captured all this information, which message, and now we have a request. You don't know how long the request took. You just said, oh, I got the request. So using TCP dump, which is a tool I used many times in this channel. Also, Wireshark is a beautiful other tool you can use. But they waited. So they parsed this. They know a request. But then to know how long a request took, you need to wait for the response, which is basically the commit. It says, hey, I got your response, whatever that is. I think we send back the position, or like an acknowledgement. Acknowledgement, we position the consumer. The producer was just send an ACK. Says, ACK, got it. So they got it. thankfully, that response has also the message ID and the topic. So they was able to, link the request with the response. And just like that, you can, they get the arrive time and they get the end time too. Okay. So you have this particular thing. Of course, there is additional time for processing the request itself. Okay. So this tells me that they did this without using TLS, because if they are TLS, they are completely blind, right? I suppose they have to decrypt it, which is, I suppose you can do, because we showed that in this channel, how to decrypt TLS traffic using curl, at least, by setting a specific environment variable, and you can decrypt it because you own everything essentially, and you tell the tool, hey, tool, write your keys, and you essentially the symmetric keys, and let the Wireshark read from those keys, and you can decrypt it. But for this, they had to disable TLS, because it's okay. You can disable TLS. I'm just what is this called? The tracing. I'm doing monitoring. Disable TLS. Who cares? Nobody's consuming my system right now. But they better hopefully enable TLS after all of this stuff, right? Especially if this whole stuff is in the cloud. All right, so we now have requests. We know the message, the return, the topic, the partition, and they learn the latency. It's 500. See, 500. This is just an example. 500 milliseconds, 500 milliseconds, 500 milliseconds. So we know they found a way to find all the slow requests. That's all what they got now. Well, by knowing the slow requests, what we need to know where is the time being spent. Now, we know that the produce is just as simply like he spends a little bit of time on Kafka, but the almost time they're just writing. So that's what they did next. They traced dynamically using eBPF, Berkeley file system, Berkeley packet filter, the write calls. Because they said, all right, Kafka's not doing much. We're just writing to the file system. So let's capture the write calls to the file system. That's what they did. So they started tracing Kafka with this approach, right? And they found that when they started capturing this, now they have, remember, we have the request, which is a request that took X amount of time, but they don't know. How do they know all of this fleet of write system, file system calls to the file system? How do they know that which write corresponds to which request? That is a really challenging thing to do, and they did it brilliantly. So they traced these ext4, because that's their file system, right? Using this ext4 slower eBPF extension. And they managed to find the right file system write calls, which is that how you write to the file system, captured it, and they know the file. But if you know the file, you know the parent directory, and guess what? The parent directory in Kafka is the topic. The file is what? The message ID? The partition. Yes, the segment file is the partition itself. So we have topic and we know the partition. So they parsed using the file name and the parent directory. They know exactly and which thread made that request, which is very important, because that's another thing. It's a multi-threaded system. So you having multiple threads competing on the same file, that's a recipe for contention. But now they have all this information. They partition ID, topic name, and here's what they built. They linked it back to the request, because if you know the topic, you know the message, you know all of this stuff, you can bring all of this together into a single beautiful table. Now they know the request, they know the latency, they know the message, they know the topic, they know the partition, and they know the latency. Okay, we know everything now. Everything is there. And all they sell is like, all right, so we can correspond how long a write call took, right? A file system write call took versus how long the request took. And if the request is equal to the amount of time to write to the file system or eventually to disk, then that whole thing, the whole request is just spent writing to disk. That's cool. And they found a lot of requests like that the entire time. Processing the request is just write, which is this, whatever, 50 millisecond, 150. But then they saw slow writes, some requests that they are slow requests, but with a faster writes. Like, what? How? There are slow requests, but with a faster writes. That means there is a bunch of space. And if you're listening to this, we're showing a graphic where there is a whole request from request to end. There's a huge, but then there is a tiny box that says, okay, the file system took only this much, but there is a big question mark. We have no idea what happened before that. And you might guess what they figured it out. It's a lock, right? And I'm not going to go into detail what that kind of lock is. Actually, you know that, knowing me, of course, I have to go into the details. But it's essentially waiting for a lock or waiting for a permission to write to the file. So before we actually did the write, we did something. We just waited. This thread it tried to attempt to do the write, to producing the write. It was just waiting. It was blocked. Why? Because, well, the file system, this comes back to the file system, guys. File system, and I talk about this in my new operating system. It's really, if you kind of dive deep into it, it has metadata, right? Because we decided that people need to work with files in directory, right? We decided that because we like directories and files. And well, what is that? This is all metadata, because there is the data you write. I won't write blocks of data. But then there is the ability to track the size of the file and the permission of the file, and this file lives in this directory, and this directory has these files, and this file, all this metadata belong to the file system that is not really user data. Well, it is, you might know what I'm saying, but if I write my produce content, like I send, I don't know, a JSON file, I don't really care if it's in this file or this directory. Yet it's a write amplification side effect, right? You decided to add this metadata just to write my stuff, right? It's on you. And this metadata has a cost. And all of this stuff is in something called an inode, an index node. And every file system implements this slightly differently. Now, this is where a file system behaves almost identically to a database. Well, file system directories and files really need to be consistent. If no two threads can delete, one thread can rename a file and the other can delete it, you cannot do that. Or one can change the content and the one can move it to another directly. You need to stay consistent. And the moment you introduce this stuff, you need to journal it. You need a wall, a write ahead log. And that's what almost all file systems are journaled, as is that all changes that you are making first are written to a different structure called a journal. It's, hey, someone on this date made this change. Someone on this date made this change to this file. That's it. And then there's the whole thing, which is the actual content and the blocks of the data, right? We don't write directly to those. Exactly like with the database we're doing. Well, in the database, we write to the wall, and then we write to the pages in memory. And then it's safe. We say, all right, we can flush safely the journal while the pages are in memory. Also up to date, of course. You have to write to them, right? But if we crash, the pages on disk are different. But that's fine. If we came back, I'll replay the journal. Is it reply or replay? Replay. I can always confuse this two. Replay. Play. To play it, we want to replay it. We want to replay all of these things back to the old last checkpoint. That's exactly how file systems work, right? To stay consistent. So that's journaling. And you cannot start journaling from two different threads on the same thing. If a transaction, and they call it also transaction, if someone is doing some changes on a file, the other threads are, especially when you're journaling, when you're committing stuff. And that is basically where most of the time is spent. You can go into the details of which kernel functions are actually doing the locking. And that's how ext4 is essentially implemented. And this is the function. It's called dirty inode. So they did all sorts of monitoring. They said, all right, what can we do? What can we make? How can we make this faster, you guys? How can we make this, more hyaku? How can we make it faster? Well, you can disable journaling. That's one option. Disable altogether. Can you do that in databases? You can. In databases, we tell you to disable fsync so that we have to journal, but we don't force you to sync those walls back to disk. It says, it's all right. It's all right if you don't. So that's one option. They said, nope, that's dangerous. If you don't journal, you are corrupt, basically, right? What they said here, without journaling, we would risk long recovery in case of a crash. I don't know if that's true. I think you're straight up corrupted, right? I don't know how you not journal and be consistent. I don't think it's possible. Because in case of a crash, while rewriting this beautiful block of data, let's say you wrote, and that's how, the LBA is presented by the disk, all right? You might write one file system block, 4 kilobyte, but it's segmented into 8 LBAs, right? So you're writing 8 LBAs, and it depends also on the physical, logical, physical sector size, how big that is compared to you, block size. That if that's out of sync, you're screwed. You're unatomic. In case of a crash, of course. Some people says, hey, I live on the edge. We live on the edge. It's okay. Yeah. We can decrease. So that's our question. Decrease the commit interval. Let's decrease it. Like how often we are flushing the wall or the journal. It's like, all right, the default is 5 seconds. Every 5 seconds, let's flush it, right? If you don't flush the kernel, the journal, you are risking what? You're risking longer recovery because you're accumulating all these beautiful wall changes in your memory. And in case of a crash, basically you lost these changes altogether, I think, right? So how often you want to commit these changes is up to you. Like it's every 5 seconds. You can reduce it. If you reduce it, you have less changes to write, of course. And as a result, you're writing more, but you're writing less. You're writing a little bit less. So if you increase it, you're not going to disk as often. And as a result, it improves the performance. They said, nah, didn't help much. They said, all right, let's change the journaling mode altogether. And instead of doing an order write, that is, let's write to the metadata and then flush the content itself. Well, let's do it a write back. That's another approach. Write back means, what does write back? Write back, it guarantees that the data is written to the main file system. So when I do an actual file write, I don't care about the metadata of the file. Write my content, later flush your metadata file system. I don't care about that. Okay. And there is an actual option in at least Postgres called if data sync. Like, well, it's a system call, but you can switch it such that, hey, sync the data, not if sync. If sync means sync everything to disk, right? Anything you have in the page cache, because everything we're talking about is almost in the page cache, right? Some of it is in the file system dedicated place for memory. But then, yeah, You're doing all this stuff. Let me write my data. That's what I care about. Your file system stuff, I don't care about. Write it later. But your risk, of course. There's always a risk involved with all this stuff. But how often all this crashes? Some people take their chances. This is all right. Let's lose some data. And some of these stuff are repairable, and operating systems, all file systems come with a repair mechanism. All right. So they did all these changes. They did a write back, and they improved from 3 seconds all the way to 800 milliseconds. So the write back improved. So the if data sync is actually very good. So you can do fast commits. That's another approach. All right. If you switch to fast commits, it's a better approach to committing those file system changes, right? So they saw some little bit of better approach. There is a little bit better performance with fast commit. They did that. So I just like this journey through the blog. It's like, hey, we're making it better. So they reduced it all the way to 500 milliseconds. But look at that. Their average seems like to be in the 250, right? That's their average, right? But now their tail latency is now way down, which is good. All right. So finally, they decided to switch all file systems altogether. And here is where I'm waiting for a part 2 of this blog, because they switch file system, and because Kafka really writes huge append only large files, they found that XFS is better. Why? I absolutely have no idea. Right? I didn't dive into the intricacies of XFS or XT4, to be honest. Right? This is something I want to do. These really, they could be. You can write a whole book about how XFS work or how XT4 work, because there is just so much more. I talk about this in an overview here as a podcast, but there's so much here. So they switched to XFS, and look at the difference here. Yeah? All of this, tail latencies, of course they show the base, right? They didn't show the changes. With fast commit, that's the latest thing. With XFS, they still saw some tail, but it caps at 500 milliseconds, just like the fast commit, but it's way better. You see, it's almost at an average. Almost, for those listening, we're seeing 20 millisecond average, maybe, perhaps less. So this is a video I wanted to make to go into the details of how you can elegantly trace the engineering art of having a problem and slowly just sculpturing it, slowly just going through every single thing and getting to the bottom of it. And they did a good job. They switched to XFS. Now, I don't think XFS has no problems. We're gonna hear back from those guys later, maybe, I don't know, in a year or two, and we always do with these things, like, oh, we switch and it's so much faster. Then they come 2 years later and says, actually, we fixed this and that broke. We fixed that and that. Yeah, it's always the case. Like, just look at Discord. Like, they moved from MongoDB to what? To Cassandra, and then to Scylla, really, right? Because every move, there was a problem to them. They saw something and then something else pops up, right? Especially as you become also popular, you get more workload, and as a result, you get more problems. More money, more problems, as they say, right? So shout out to them guys. Great. Masij Mosiki, and then Petor Raisko. You guys, that's a fantastic blog. I can encourage you to read it, and not only read it, read the links. You guys read the links. They provide a beautiful, resources. You know, all these links, they say, hey, we found this tool. It's called Async Profiler. We found this tool, I don't know, XT4, whatever, you know, slower. That's the ePBF. And we wrote this and we wrote that. I really hope they upstream their changes to Kafka. Now, how did they, you know, capture the request all the way to the file system? This is really, I don't think it's like a one tool. It's like they use many tools, and to link this together is like, it's going to be really nice to have this in Kafka. You know, they actually contemplated the idea to contribute. They fork Kafka, add the logging, and then put it back. But even that will not give them the file system, you know, timing, because you don't have access to that low level thing. No. Do you? Yeah, because you're just making a boop. You're making a POSIX write, and God knows the kernel does billions of things before it does your actual write, right? All right, guys, that's what I wanted to talk about. Yeah, we're back. Sorry about the hiatus. I've been working, as you might know, my operating system course, and it's been taking a long time with family and all that stuff. But yeah, hopefully we came back to the cadence, producing more content. And thank you so much. And check out the course. It's os.husseinnasser.com. Fundamentals of Operating Systems. It took 2 years to build, from all the building the content and actually going through all this stuff. See you in the next one.